Welcome back to Geometry, Measurement, and Probability. In this section, section 9.2, we're going to focus on multi-stage experiments and independent events, as well as conditional probability. So let's get started. We began by talking about multi-stage experiments. These are experiments that are completed in multiple steps, such as flipping a coin twice or rolling a die twice. Now, some multi-stage experiments are done with replacement and some are completed without replacement. First, let's suppose we toss a fair coin 3 times, and I want to think about the sample space for this event. Now remember from section 9.1, a sample space is a set, and so we use the wavy braces to represent a set. Now if I toss a coin 3 times, I might toss 3 heads. That's one possible outcome. Or maybe I toss 2 heads and then a tail. Maybe I toss a head and then a tail and then a head. Or maybe the tail comes first, followed by 2 heads. I could also toss 3 tails. Or maybe I toss 2 tails and a head. Maybe the head's in the middle of the 2 tails. Or maybe the head comes first. And notice here that we have 8 possible outcomes. In part B, we're asked to find event A, or the event of tossing 2 heads and a tail. So I'm going to look at my sample space and I'm going to list all of the outcomes that have 2 heads and 1 tail. Again, our events are sets, and so we list them in the wavy braces. So I have 2 heads and a tail. I have head, tail, head, or tail, head, head. These are all the possible outcomes with 2 heads and 1 tail. Now, look at part C. Event B is the event of tossing no tails. Well, if I toss no tails, that means everything is heads. So that would be heads, heads, heads. Again, our event, the outcomes are a set, and so we list them in the wavy braces. Last, we have event C, the event of tossing a head on the last toss. So go back and look at your sample space. List all of the outcomes in the sample space that have a head on the last toss. So that would be a head, head, head. That might be a tail, head, head. Head, tails, head. Tails, tails, head. Those are all of the outcomes in my sample space that have a head on the last toss. Now, let's start thinking about multi-stage experiments with replacement. So let's suppose I have a box that has 2 white marbles and 1 black marble, or 1 black ball and 2 white balls. Suppose a ball is drawn at random from the box. We record the color and then we replace the ball in the box and we draw a second marble. And so our sample space for this experiment is 2-stage because I'm drawing 2 marbles. Our sample space, I could draw a black marble and a black marble. I might draw a black marble first and then a white, or a white marble and then a black marble, or maybe 2 white marbles. Now when I'm looking at the probabilities, I'm going to trace along my tree diagram. The probability of drawing a black and then a white. Follow your tree diagram. The probability of drawing a black is 1/3, and then the probability of drawing a white, notice, is 2/3. Along the tree diagram, I multiply my probabilities. So I would say 1/3 times 2/3. Multiply the numerators gives us 2, and multiply the denominators gives us 9, and we have a probability of 2/9. The next one asks us for the probability of drawing black, then black. So I'm going to follow my tree diagram. Notice I'm circling this time in blue. So probability of black and then black. We have 1/3 times 1/3. Multiply the numerators, then multiply the denominators, and that gives us a probability of 1/9. Then finally, we are asked to find the probability of white, then white. Now you'll notice this time I circle the probabilities in black. So the probability of drawing a white is 2/3. And I multiply 2/3 times 2/3, multiply the numerators gives us 4, and multiply the denominators gives us 9 for a probability of 4/9. Our multiplication rule for tree diagrams is this. The probabilities is the product of the probabilities along the path on the tree diagram, just like we saw in our last example. In example 2, we have a box that has 3 red balls and 2 blue balls. We're drawing a ball at random, recording the color, and notice again that we are replacing the ball in the box, and then we're drawing a second ball and recording the color. So let's think about our tree diagram for this experiment. I want to think about my first draw. Well, I might draw a red or I might draw a blue. Now let's think about the second draw. If I draw a red the first time, I could draw a red the second time, or I might draw a blue the second time. The same thing happens if I draw a blue on the first draw. I might draw a red or I might draw a blue. So follow your tree to list the possible outcomes. We'd have a red and a red and a blue and a red, or maybe 2 blues. Now let's think about our probabilities. First, I need to know how many total balls are in the box. Well, 3 red balls plus 2 blue balls is a total of 5 balls. So my probability of red would be 3 out of 5 because there's 3 red balls and 5 total. I'm going to go ahead and list these probabilities on my diagram. The probability of drawing a blue is 2 out of 5 because there's 2 blue balls out of 5 total. And I'm going to list the probabilities everywhere there's a blue. To find the probability, remember we multiply across our tree. So for red, follow your path, 3/5 times 3/5, that gives us 9/25. For a red and then a blue, we have 3/5 times 2/5, multiply the numerators, multiply the denominators, gives us a probability of 6/25. For blue and then red, we have 2/5 times 3/5, follow your path on your tree diagram. 2 times 3 is 6 in the numerator, and 5 times 5 is 25 in the denominator. And then last we have blue and blue. 2/5 times 2/5 gives us 4/25. Now, look at part B. We're asked to find the probability that the balls are different colors. So let's think about the outcomes that have different colors. One outcome was a red and a blue, and then the other was a blue and a red. There is no overlap with these 2 outcomes, and so we can add the probabilities. Look back at our list. The probability of a red and a blue was 6/25. The probability of a blue and a red was also 6/25. Because we have a common denominator, we add the numerators, gives us 12/25. Look at part C. What is the probability that the balls are the same color? Well, first, I want to list the possible outcomes. So I might have a red and a red, or I might have a blue and a blue. Again, let's look at our probabilities. The probability of a red and a red was 9 out of 25. The probability of a blue and a blue was 4 out of 25. The denominators are the same, so we can add the numerators. This gives us a probability of 13/25. Let's think about independent events. Independent events mean they don't influence each other, like tossing 2 coins or rolling 2 die. The outcomes of tossing 2 coins don't impact each other, or the outcomes of rolling 2 die don't impact each other. Now, event A is at rolling double sixes. Notice there's 1 pair of double sixes. This is 1 pair, 1 outcome, out of there are a total of 36 outcomes. There are 6 pairs across times 6 pairs down is a total of 36. Now look at part B. Many times with rolling dice, we think about their sums. So rolling a sum of 7 or 11. Now these 2 outcomes don't overlap, so I can add their probabilities. Circle all the pairs that have a sum of 7. There are 6 of them out of 36 total pairs. Now circle all the pairs that have a sum of 11. There are 2 of them, so our probability is 2 out of 36. The denominators match, so add your numerators. We get 8 out of 36. And always simplify your fractions. 4 goes into 8 2 times, and 4 goes into 36 9 times. Get example 4. Again, we're thinking about rolling a pair of fair dice and recording the sum. But this time, event E is an even number, and event F is a prime number. There is an overlap between E and F. So when we're finding the probability of E or F, we have to use the formula that we learned in section 9.1. The probability of even plus the probability of prime minus the probability of both. So let's look at our sums. How many of those sums are even? I'm going to circle all of the even sums. There are 18 even sums out of a total of 36. Plus, let's look at all the sums that are prime. 2, 3, 5, 7, and 11 are the prime sums. There are 15 prime sums out of 36 total. Minus, notice there is one sum that was circled twice. So the probability of both is 1 out of 36. The denominators match, so add and subtract the numerators gives us 32 out of 36. Always simplify your fraction. Goes into 32 8 times, and 4 goes into 36 9 times. Independent event. Remember, independent means they don't impact each other. We multiply their probabilities. So look at example 5. Suppose we toss a coin 2 times and we record the results. First, we want to know the probability of tossing a head and then a tail. Well, a head is 1 out of 2 possible outcomes, times a tail is 1 out of 2 possible outcomes, so we have a probability of 1/2. Multiply your numerators gives us 1. Multiply the denominators is 4. Look at part B. The probability of tossing 2 tails. The probability of tossing a tail is 1 out of 2 possible outcomes times 1 out of 2 because I'm tossing 2 tails. Again, multiply the numerators and multiply the denominators gives us 1/4. In the second video, we'll pick up with multi-stage experiments without replacement.